Dear students, this is a continuation of our previous video. Now we have to find this phi double dash of x, for which we will be using the fact that phi is a solution of this ordinary differential equation. Now if phi is a solution of this equation, it means that it must satisfy this equation. That is, L of phi is equal to 0. So we know that L of phi is equal to 0. The reason behind is phi satisfies L of y. That is, it is a solution of L of y. So because of that, L of phi is equal to 0. But what is L of phi? You have to replace the variable y. Instead of y, you should replace and write it as phi. So we will have phi double dash plus a1 phi dash plus a2 phi to be equal to 0. So let us write that over here. So we have phi double dash plus a1 phi dash plus a2 phi is equal to 0. So from this we can obtain that phi double dash is equal to, taking these two terms to the right hand side, we get minus a1 phi dash minus a2 phi. Now let us take the modulus on both the sides. So when we take modulus on both the sides, it becomes modulus of phi double dash is lesser than or equal to. Now this negative sign becomes positive when we take modulus. So it becomes modulus of a1 multiplied with modulus of phi dash. And this also becomes positive, so it is plus modulus of a2 modulus of phi. So therefore we arrive at the following equation. So phi modulus of phi double dash of x is lesser than or equal to modulus of a1 modulus of phi dash of x plus modulus of a2 and modulus of phi of x. So let us mark this as equation 3. Now this equation 3 has to be substituted in this equation 2. In place of phi double dash of x, we will be substituting this value. And we have lesser than or equal to in both the cases. So directly we can substitute here. Now let us substitute the equation 3 in equation 2. So we get modulus of u dash of x is lesser than or equal to twice modulus of phi of x modulus of phi dash of x, okay, plus twice modulus of phi dash of x and modulus of phi double dash of x, I will write it here in bracket. So it is modulus of a1 multiplied with modulus of phi dash of x and then plus modulus of a2 multiplied with modulus of phi of x. So this is after substitution we have got this. Now let us multiply this 2 modulus of phi dash of x inside these two terms. That is, we should multiply with these two terms. So we get modulus of u dash of x is lesser than or equal to 2 modulus of phi of x modulus of phi dash of x plus twice modulus of phi dash of x into modulus of a1 into modulus of phi dash of x plus twice modulus of phi dash of x into modulus of a2 into modulus of phi of x. Now if we see in these two terms, so when we see these two terms, we have 2 and then phi of x phi dash of x common. So when we take it common outside, we get modulus of u dash of x to be lesser than or equal to twice modulus of phi of x, modulus of phi dash of x into 1 plus modulus of a2. And then in this term, these two terms are same. So when multiplied, it becomes square. So we get plus twice modulus of a1 modulus of phi dash of x the whole squared. Now after this, in this we could replace this by using an inequality which we know. That is, we know that twice modulus of b modulus of c is always lesser than or equal to modulus of b squared plus modulus of c squared. So let us use this inequality over here, where this term is like b and this term is like c. So when we use that inequality over here, we get modulus of u dash of x to be lesser than or equal to. So anyway, here also we have lesser than or equal to. So this becomes modulus of phi of x the whole squared modulus plus modulus of phi dash of x squared, okay, multiplied with 1 plus modulus of a2, and this remains the same. So plus twice modulus of a1 modulus of phi dash of x squared. Now let us multiply these terms along with this. So we get modulus of u dash of x to be lesser than or equal to, now this multiplied with 1. So modulus of phi of x the whole squared plus this multiplied with this. So modulus of a2 modulus of phi of x the squared. Now let us multiply this term with these two terms. So we get plus modulus of phi dash of x squared plus modulus of a2 phi dash of x squared plus twice modulus of a1 modulus of phi dash of x squared. Now we observe that in these three terms, that is not this, in these three terms phi dash of x the whole squared is common in these three terms. Okay, so this term and this term. So when we take that common in these three terms, we get, and also in these two terms phi modulus of phi of x is common. So we observe that in these two terms phi of x is the whole squared is common, and then in these three terms phi dash of x the whole squared is common. So when we write by taking whatever is in common out, we get modulus of u dash of x to be lesser than or equal to, this one we get it as 1 plus modulus of a2 multiplied with modulus of phi of x squared plus, similarly here we get 1 plus modulus of a2 plus twice modulus of a1 multiplied with modulus of phi dash of x the whole square. Now in this equation, these two are near constants. They doesn't make any much significant when they are changed, because we have the inequality lesser than or equal to. Now let us bring it into common terms. So for that, actually in the question we have k is equal to 1 plus modulus of a1 plus modulus of a2. Now this is given in the question. Now let us bring these two into those two same format. So when we, because they are mere constants and we have the inequality, that doesn't change the equation into any large difference. So it becomes modulus of u dash of x. We can write this inequality by taking these two terms common and considering it to be this. Because it doesn't make any big change, we can write it as 1 plus modulus of a1 plus modulus of a2. And then the terms out there will be this plus this. So modulus of phi of x squared plus modulus of phi dash of x squared. So the reason of writing this is these are constants which are mere constants, and we have the inequality, and in the question they have given the value of k to be equal to this. So in order to bring a solution with a value k, we are just you could think that we are adding or subtracting whatever is required and bringing it into a common term, and we have made it like this. Now this can be replaced as k, and therefore we get modulus of u dash of x to be lesser than or equal to some k, this k multiplied with modulus of phi of x squared plus modulus of phi dash of x squared. But from the given question, we know that the square root of this is norm phi of x, and therefore this term will be equal to norm phi of x the whole squared. This we have taken from the question. So therefore we will get it as modulus of u dash of x to be lesser than or equal to k into norm phi of x squared. So after this, we can see that in analysis we know that if a term has this, for example, if we say x is lesser than or equal to 1, we actually mean that is if we say if modulus of x, if the absolute value of x is lesser than or equal to 1, we mean that x lies between minus 1 and plus 1. So x is greater than or equal to minus 1 and lesser than or equal to 1. So this is a concept from analysis. Now we will be using this concept over here. Now we know that this term is lesser than or equal to this term, that is modulus. Particularly we should have that absolute value. If we have the modulus only, we can apply this concept. So because we have modulus over here, this can be written as minus k norm of phi of x squared is lesser than or equal to u dash of x, which is lesser than or equal to k norm of phi of x squared. And after this, for our convenience, we change the value of k to be 2k. So what we do is we replace k by 2k for our convenience so that we get the required answer. And that also doesn't make any change because we have the inequality sign over here. So this becomes minus 2k norm phi of x squared is lesser than or equal to u dash of x lesser than or equal to 2k norm phi of x squared. In the beginning of our proof, we have considered norm phi of x squared to be u of x. So this can be written as minus 2k u of x is lesser than or equal to u dash of x, which is lesser than or equal to 2k into u of x. Let us mark this as equation 4. Let us consider this inequality and proceed the proof further, which will be done in the next video. Thank you.